So far I've only looked at hypothesis testing where the most complicated of two models has won the day, and this may seem eminently reasonable. If Model 2 has more degrees of freedom or parameters than Model 1, then Model 2 should be able to describe every outcome that Model 1 describes and more. The model can be made to fit the data better if it has more things to fiddle with. But in probabilistic reasoning, a model isn't judged by how well it can fit the data, it is judged by how well it predicts the data. And that's a big difference. Now, if a model has enough room to maneuver that it can predict some possible data outcomes better than other, more simpler models can, then it must be that there are other possible data you could get where the simpler model predicts better. Since probabilities of outcomes under each model should sum to 1, then if you can get evidence for the complicated model, you can get evidence for the simpler one too. Now, if a model has enough room to maneuver that it can predict some possible data outcomes better than another more simple model can, then it must be that there are other possible data you could get where the simpler model predicts better. Since the probabilities of outcomes under each model should sum to 1, then if you can get evidence for the complicated model, you can also get evidence for the simpler one too. This can be illustrated by the probability of outcomes for n equal to 100 repeatable independent trials, i.e. a binomial model, when the success rate is fixed at p equal to 50%. The more complicated model, where the success rate p is 3, has another probability distribution for the possible outcomes. With a particular probability distribution I've chosen for p, where each value of p is equally probable, the distribution of each possible outcome is flat under Model 2. If the outcome is less than 40 or greater than 60, we have a situation where the probability for getting that outcome under Model 1 is less than the probability of getting the same data under Model 2. So we can get evidence for Model 2. But as you can see, there's another region of possible outcomes where Model 1 predicts better than Model 2. Okay, that's the theory so far. I think it's high time we took a peek at a practical example. As the first hypothesis testing video was a dragon versus knight scenario, I think it's high time we took a trip back to the game Age of Wonders. This time I've given each player 100 dragons though. The question is, does player 1 has the same success rate as player 2? There could be some advantage in being the attacker, for instance. As the dust has settled, player 1 is left with 52 dragons while player 2 has only 48. Now, if we cut back to the predictions of each model, you can readily see that Model 1, the simpler model, has 1. The probability of getting such data is 7.4 times better under Model 1 than under Model 2. If we assigned each model a prior probability of 50%, we would end up with a probability for Model 1 of 88.1% after the data. We've seen earlier that the free model, Model 2, can for some datasets learn from the data already received and use that in order to predict the next outcomes better. But what if there's nothing to learn? What if we get data that Model 1 describes beautifully? Then the freedom in the extra parameter in Model 2 only gives rise to extra uncertainty about the outcome. And extra uncertainty means less prediction power, and by Bayes' formula, less prediction power means lower posterior probability. Getting evidence for a simple model is something I can find no parallel in frequentist hypothesis testing. You only reject or do not reject models there, and you can't reject a complex model for one with less degrees of freedom. You can reject a simple model, but if you haven't, then the status is the same if you got 10 or 1,000 trials. In Bayesian statistics, you can bolster your confidence in a simple model though, as we've just seen. Let's take a trial-by-trial look at this like we did in clip 20. Again, I show 4 plots per trial. The outcome of the trial is shown in figure 1 with a dot for 0 and a line for 1. The next is the prediction probabilities for 0 and 1 under model 1 and 2. with the outer black representing the dynamic predictions from Model 2, while the inner red are the static 50-50 probabilities of Model 1. The third plot is the posterior model probabilities, which starts at 50% for each. The fourth plot is the probabilities for P under Model 2 after processing the trial. After the first trial, where player 1 won, and where each model predicts that equally well, Model 2 adjusts the probability for P to the high end of the scale. So the next trial, which also ended in victory for player 1, is better predicted by Model 2 than Model 1, and Model 2 increases in probability. However, when the third trial doesn't go that well for player 1, this comes as a surprise under Model 2, which has adjusted itself so that this outcome only has a 25% chance. Model 1 makes a huge leap forward. The battle between Model 1 and Model 2 rages on, as shown in this animation of the 100 trials, with the posterior probabilities going a bit back and forth, though generally in Model 1's favor. In the end, there's only one victor, and that's Model 1. Here's a plot of the base factor as a function of the number of trials so far. I've also plotted an expected base factor for data produced by Model 1, attained via simulation. As you can see, we don't get the extreme base factors we get when the simpler model was rejected. Getting evidence for a simpler model is a bit of an uphill struggle, as you can see from this graph. Now, the resulting base factor doesn't mean that the simple 50-50 model necessarily is the one true model for this scenario. But it does mean that with all things being equal, the data suggests that we are better served with Model 1 than Model 2. We've got evidence for a 50-50 success rate against a model where the success rate can be anything. Some may argue that since we got evidence for P equal to 52% in Model 2, that must have been the value for P all along, and since the observed rate is more probable there than under P equal to 50%, we got evidence for Model 2. Hopefully you can recognize the circularity of this argument. Still, it's a nice way to start looking at this from another angle. Let's plot the data likelihood under different submodels of Model 2, i.e. different values of P. I've also plotted the data likelihood under Model 1 as a horizontal line. Let's zoom in on the part of the plot where the observed rate is. As we can see, there's a range of values of P which gives a greater data likelihood than the simpler P equal to 50% model. It's a narrow band stretching from P equal to 50% to P equal to 55%, peaking at 52%. There's a small subset of Model 2 though, which gives an equal prior probability to all values of P ranging from 0 to 1. If we make a slightly larger interval around P equal to 52%, ranging from 48.5% to 55.5%, we have a submodel of Model 2 which in average gives the same data likelihood as Model 1. But that's not the whole of Model 2. There are two other submodels of Model 2 where the data likelihood is lower than for Model 1. So that's one submodel with equal data likelihood as the alternative model and two submodels with lower data likelihood. From the principles in clip 5, the shrinking model family, that means that Model 2 must get its probability lowered by the data. Since the standard deviation of the observed rate decreases proportional to the square root of the number of measurements, one can guess that approximately the expected base factor increases with the square root of the number of measurements, given that the data is produced by Model 1. So you need 4 times as much data to get twice the evidence. An uphill struggle, as I said. Just a peek at another example in the end. As in clip 21, I'm looking for the probability of rolling a 6 on a die, but this time with another die which I do not think is loaded. But let's anyhow give each model an equal chance. Model 1 says that P equal to 1 over 6. Under Model 2 I use a prior probability distribution for P that's centered around P equal to 1 over 6. The reliability of the experiment gets lowered with P different from 50%, so I did 400 trials rather than 100. The predictive distribution of the two models are plotted here. I got an outcome of 86s, which is in the thin end of results suggesting p equal to 1/6. Still, any base factor greater than 1 is evidence for model 1, and in this case I've got 2.4. So the data suggests that this indeed was an unloaded die. I hope you now can see that a simple model may win, when the other extra adaptivity of a more complex model doesn't compensate for the extra uncertainty introduced by the added degrees of freedom.